remember what resistance is in an electric circuit? It is something that controls the flow of current. If it's more, then the current reading will be lower, and if it's less, then the current reading will be higher. It's inversely proportional to the current. Let's talk a bit more about resistance. What are the factors on which a resistance of a conductor depends? When can we say that the resistance of a conductor is more or less than that of another? Let's do a small activity to understand this. Take a small electric circuit like this one, which has a plug key, a power source and an ammeter. In the first case, connect a nichrome wire between these 2 points. Let the length of this nichrome wire be a lowercase l. Now plug the key and measure the reading in the ammeter. Now let's try playing with the factors a bit. In the second case, we double the length of the nichrome wire, but keep the thickness same. We just double the length. When you measure the reading, you will notice that the current is half of the current measured originally. When the length was doubled, the current halved. In the third case, we replace the wire with a thicker nichrome wire with length L. Understand this case well. We're just increasing the thickness of the wire without changing the original length L. Now, if you're increasing the thickness of the wire, it simply means we're increasing cross-sectional area. Let's call it A. Now, when you measure the current, you will notice that it's more than the original current I1. The results we're getting are pretty interesting. Let's try out one last case. We use a copper wire instead of a nichrome wire. The length and cross-section area A will be the same as the original wire, but the material has changed entirely. When you measure the current, you will notice that it's more than I1. Now let's understand the results case by case. We see that as the length of the wire increases, the current reduces by the same factor. It implies that the current is inversely proportional to the length of the wire. And by Ohm's law, we know that the current is inversely proportional to the resistance of the conductor. So these two together will imply that the resistance R is directly proportional to the length of the wire. More the length of the wire, more will be the resistance. Note that here we assume everything else will be constant. It'll be the same wire and it'll have the same cross-sectional area, and other factors like temperature will also be constant. So the length of the wire is one of the factors on which the resistance of a conductor depends. The resistance of a conductor is directly proportional to the length of that conductor. The third case tells us that as the thickness of the wire was increased, the current flowing through it also increased. It tells us that the current flowing through a conductor is directly proportional to the cross-sectional area of that conductor, which means that the resistance will be inversely proportional to the cross-sectional area of the conductor. Combining these two tells us that the resistance is directly proportional to the length of the conductor and inversely proportional to its cross-sectional area. If we introduce a constant ρ, it can be written like this. This is the constant of proportionality and is called the electric resistivity of the material of the conductor. In the fourth case, we saw that as the nature of the material changes, the current flowing through the conductor also changes. And that's because as the nature of the material changes, its electric resistivity also changes accordingly. Conductors, for instance, have lesser resistivity as compared to alloys, and alloys have lesser resistivity as compared to insulators. Nichrome is an alloy, while copper is a metal which is a good conductor of electricity. And that's why the current reading increased when the material changed to copper. The SI unit of resistivity is ohm meter. How is it ohm meter? We can look at this formula and deduce it. The unit of resistance is ohm, the unit of length is meters, and that of area is meter squared. Cancelling and transposing the units gives us the SI unit of ρ as ohm meter. We will understand resistivity in detail in the next video. But before we end this video, let's quickly review what we learned. The resistance of a conductor is directly proportional to its length and inversely proportional to its cross-sectional area. And it also depends on the nature of the material. If the material has low resistivity, its resistance will be lower, and if it has more resistivity, its resistance will be higher.